The definition of impulse is the change in momentum. This is a little confusing because in common day language we don't use the word impulse to describe a change in momentum. We usually use it to describe a force, which is not the case here. An impulse is a change in momentum, a final momentum minus an initial momentum. If the momentum of an object does not change, the impulse is zero. If it starts with a certain impulse and ends up with a different, it starts with a certain momentum and ends up with a different momentum, then there is an impulse. The impulse is the change in momentum. Okay, now let's take this example here. I took this from the Teacher Source website. It's an image of two types of small balls that they sell. One of the balls, they call it the happy ball, and the other one is the sad ball. The happy ball is somewhat like a super ball. When you drop it on the floor, it's going to bounce back almost to the same height you dropped it from. And here they are exaggerating, making it look like it's going to come up to the same height, but it comes close to the same height. Now the sad ball, on the other hand, is going to be a ball. Once it's going to hit the ground, it's going to stop. It's not going to bounce at all. That's why they call it sad. What's the change in momentum for each one of them, or which undergoes a bigger change in momentum or a bigger impulse? Okay, if we discuss this one, so we are letting them off, both of them vertically, so ignore the angle here, please. Just that's for visualization to show us that it's going down and then back up, while this one just doesn't go back up. So it's vertical motion only here. That's what we have. Now, since we drop them from the same height, both of them are going to have the same velocity, and in this case they have the same mass, so they are going to have the same momentum just before hitting the ground. So their momentum before hitting the ground, if I call it P1 for this one, it's going to be P1 for this one. Okay, note that I put the direction for both of them. Momentum is a vector, remember, so it's pointing down in both cases. Now this one is going to bounce up. If it's going to bounce up and be able to go to the same height, that would mean that it should have the same velocity upwards, and since it has the same mass, that means it's going to have the same momentum in the upward direction. However, it's opposite in direction. P2 is going to be equal to P1, but in the opposite direction. Now, P1, for the sad ball, the final momentum is going to be 0. Now, for the happy ball, the change in momentum is going to be P2 minus P1. Now, if I take the upward direction as positive, my P1 is going to be negative and my P2 is going to be positive. So here it's going to be P2 minus P1. And here my change in momentum is going to be equal, again, P2 minus P1. So it's going to be 0, since P2 is 0, minus P1. Okay, now in this case, what's P2 minus P1? Now remember, both of these, P1 and P2, have the same magnitude. They have opposite directions, but they are same speed and same mass, so same mv. But P1 is negative and P2 is positive. So if I call P2 mv, my P1 is going to be minus mv. So this is going to be mv minus mv. So it's going to be twice mv, because the minus gives me a plus, so plus mv plus mv is twice mv. And in this case, it's going to be 0 minus mv. So it's going to be just mv. So you notice here that actually the one that does not bounce undergoes a smaller change in momentum or a smaller impulse than the one that bounces. There are interesting implications to that. For example, if you are going to try to hit something here and make it fall off, you are going to be able to exert a bigger impulse by hitting it with a ball that's going to bounce than with a ball that does not bounce, for example. Okay, we'll see another implication in a little bit. Now, another definition of impulse, it is equal to the average force that's responsible for that change in momentum times the time during which that force is going to be acting. So the change in momentum that we talked about earlier as momentum final minus initial momentum is also equal to the average force responsible for that change in momentum times the time. Remember, when I have an object that has a certain velocity, it's going to have a certain momentum mv. Remember Newton's first law. It says the velocity is not going to change unless we have a net force. Now, in this case, if the velocity does not change, that means the momentum does not change, which means the momentum of an object will remain unchanged unless we have a net force, a net external force acting on the object. That's what we are talking about here. This net force times t. Now, why do we write it F average with a bar on top instead of just saying net force? Because actually, the forces that act on an object to change its momentum can be very complex in nature, and their values change quite a bit over a very short amount of time. That's why we are saying the average force. We are not having to worry about the value of the force at a particular instant, but we worry about the overall force that has acted to result in the overall change in momentum. When we start looking at the pictures and the videos coming in the next screens, you should see what I mean by intricate force. Before we get to that, look one thing at this equation. We have the impulse average net force times time. Now, it's an equal sign that tells us if t is small, then F is large for the same change in momentum. If t is large, F is small, again for the same change in momentum. If we need a particular change in momentum, like the ball hitting the floor and bouncing back with a certain speed, if we need to have the same change in momentum, then if I'm going to apply a force for a short time, then I need to apply a large force. If I'm going to apply a force for a long time, then I can apply a small force. Now, examples of this, for example, if you have a ball in your hand, so its momentum is 0 if it is in your hand, and you are going to toss it. So your hand is going to be responsible for the net force. So if you apply that force for a long time, then you can give it a large enough speed, and by giving it a large enough speed, you can give it a large enough momentum, so you can obtain a certain impulse. If instead you are going to hit it with a bat, for example, that bat, like a baseball bat, that's not going to exert the force for a long time. It's going to exert the force on the ball for a short time, and result in the same momentum or even larger momentum. So then it has to exert a larger force over a short time to obtain the impulse, while you exert a smaller force over a longer time to get the large impulse. Okay, now just a few pictures here. Look at a baseball bat on a baseball. Look how it affects the shape of the baseball, how it deforms it. That gives you an idea of how strong the force is that the bat is exerting on the ball. So actually, the ball, the minute it touches the bat, was spherical in shape, and then it's going to bend till it reaches about this shape here, and then it's going to regain its shape and bouncing back, bouncing off the bat and moving off. So in this particular case, what we have, a ball coming from this shape to the shape that we are seeing here. And then it's going to go from this shape that we are seeing back to the other shape. Now, the actual average force that started acting on the ball from the instant it touched the bat to the instant it is off the bat, that's what we designated as F, like this. And the time the ball was in contact with the bat, that's what we designated as T. F times T is going to be equal to our impulse. Okay, now you can see, you might think that golf balls are harder. You see the same effect here. Okay, so actually, the club is going to hit it with a strong enough force to cause that kind of deformation. You see, the ball didn't even move yet. The force was so large to deform the ball that way before there is any motion. Then what's going to happen, for over a very short time, the ball is going to rebound through the elasticity of its material. It's going to rebound back, regain back its shape, and bounce off the club. Okay, easier case here. I think I misspelled rugby. I think it's with you. I think this is a rugby ball, not a football, but you might know better. They don't look like football shoes to me, or we don't see the rest of that type. Okay, you see the effect. Okay, now you see it here on a tennis ball. Look at the shape of the ball, it's almost halved. But notice the effect also on the racket. So the racket is also, the action-reaction pair. The ball exerts a force on the racket exerts a force on the ball. And these two forces are huge forces. That's what we are talking about, because the contact time is a very short time. Ft. Short contact time, large force. Okay, let's look at this video here. Short video. Okay, look at the ball there. Okay, look there. Okay, see, this is a billiard ball. Let's see if we can replay it. Okay. Look at the impact on the rail. Okay, in this case, the ball is quite hard, but the rail is not that hard. So the rail is going to bend much more than the ball bends, and it's going to help the ball bounce back. Okay, now, implications of this. For example, if you are playing catch, I'm almost sure that most of us played it. You see how these kids, when they catch the ball, they give. They don't catch it just in place. Okay, when they give, what they are doing, they are extending the time it's going to take to change the momentum of the ball from whatever momentum it has while it is moving to the momentum it will have when it will stop, which is a zero momentum. So the change in momentum is from a particular momentum to zero. Now we extend the time. So when we extend the time, what that means is the force does not have to be as large that we exert on the ball. So we don't exert a large enough force on the ball, which means in turn the ball will be nice to us and will not exert the reaction to the force we exert on it. So it will not exert a large force on us. So it will not hurt to catch a ball. Okay? Now, let's take this example here. In this case, these kids, I believe they are in a high school. What they are going to do is try to toss an egg on this sheet here. Let's see what happens. It's a raw egg, by the way. Okay, they hit it again, and it does not break. In this particular case, if I extended the video longer, we will see what happens when they miss the sheet. But it was not a good enough video to show that, so I selected this other video to show that. Okay, now in that case, we saw the ball on the ground when someone missed the sheet, and there you see the effect in the classroom. That happened to me quite a bit, actually. Okay, we play it again. Okay, that's when someone misses the sheet. So it's a raw ball, a raw egg. So it is a raw egg, and if it hits the sheet, because it is flexible, is going to give, and giving is going to extend the time needed to stop the egg. By extending the time, we don't need as big of a force, so we don't use a large enough force to stop the egg, so that force is not large enough to break the egg. However, if we have a wall like here, the wall is not going to be able to give, so it's going to immediately stop the egg. By immediately stopping the egg, it's going to exert a large force. The word immediate means a very short time. Short time, large force, large enough force to break the egg. Okay. This is a very interesting thing. I didn't see this till I was preparing for this lecture. This brave guy is going to allow some other guy to slap him on the face, and they are actually videotaping this in slow motion. See the effect of a slap, a normal slap that I personally got some slaps on my face in my life, so probably I would think some of you have experienced some of that, and you see really what happens. You see the hand coming. Look what happens to the face. So it's a force, a large force over a short amount of time. So that resulted, in this case, the face can deform very easily, and it's not a sturdy thing.